Good. Thank you very much for the introduction, and thank you for the invitation. I'm very honored. Unfortunately, I couldn't be here as you mentioned, and I was really looking forward to it because I've never been to Iceland, but I wish you a very joyful and wonderful conference. So yes, this is a joint work. So I'm going to talk about intuitionistic logic and beyond that, and the role of quantifier shifts. And this is a joint work with these people, Matthias Baz, Raheleh Jalali, and Mariami Gamskurdia. And all these photos are taken from their websites. So yes, let me start by talking about motivation. And after that, after motivating why we are doing this research, we are going to talk about the logic that we are interested in. And finally, we are going to give our main result. So let me start by a general practice. Suppose you are proving a theorem in mathematics, and in the process of proving a theorem, you get for each x there exists a y such that a of x and y holds. Then it is convenient for you to introduce a fresh function, a new function f, that picks a y for each x such that a of x and f of x holds for each x. So consider this general practice, consider this example, and then what we are going to consider is something about this general practice, about what is called a Skolemization. And first, I wanted to say that it is defined either in the context of derivability or satisfiability. So in the model theoretic view, we replace existential quantifiers by new function symbols, like the general practice that we saw here. And then what we get in the end is some formula that is satisfiability equivalent to the formula that we started with. And the proof theoretic view is something on the opposite. We replace universal quantifiers by new function symbols, and what we get is a validity formula, which is validity equivalent formula, which is equivalent to the formula that we started with. And not only because I'm a proof theorist, but also because we are considering a Skolemization for any logic in general, we would like to choose the proof theoretic view. So this is the definition of a Skolemization, which is not the very formal definition. And this person here is Skolem. So the proof theoretic view to Skolemization, we define it as the following, that there is a method to remove the strong quantifiers, and by strong I mean positive occurrences of the universal quantifiers and negative occurrences of the existential quantifiers. Again, I'm not defining these notions formally, but they can be defined formally by recursion. So it is a method to remove strong quantifiers from a first order formula phi, and we replace them with fresh function symbols. And the result is called the Skolemization of phi, and it is denoted by phi to the s. So let's see an example what I mean by Skolemization and by removing strong quantifiers. So suppose I have a formula for all x, there exists y for all z, phi of x, y, z, and I want to get the Skolemization of this formula. So this method, we are removing strong quantifiers. This is a positive occurrence of universal quantifier. So for all x is positive, for all z also positive, and suppose that phi is quantifier free. Then the Skolemization of this formula is going to be there exists y, phi of c, y, and f of y, where c is a new constant and f is also a new function symbol. And because this c was in the range of y, this f of y, f is related to y. So yes, the idea goes back to Skolem, and this Skolemization works well in classical predicate logic CQC. But an intuition that I have when I look at the Skolemization in classical logic is that, in a sense, Skolemization is blind with respect to the place of the strong quantifiers, which means that whenever in a formula you have some strong quantifiers, without looking at the place of the strong quantifier, the method just goes to the universal or strong quantifier, removes it, and replaces it with a new function. And because of this intuition that we have, and we know that it works well for classical logic, the first impression when you think about the skolemization in intuitionistic predicate logic IQC is that it may not work, because we know that it's not the case that every formula has a formula equivalent to it, which is in pre-next normal form, meaning that all the quantifiers are at the beginning of the formula. Or in other way, we know that all the quantifiers and connectives do not commute freely. We know this fact about IQC, and because of this, we expect that skolemization is not easy. And indeed, this is the case. So for intuitionistic logic, as well as many super-intuitionistic logics or intermediate logics, skolemization is non-trivial. Yes. So before talking about related work, I wanted to give you a definition, which is the following, that we say skolemization is sound and complete for a logic L. So soundness is direction from left to right, and completeness from right to left. When for any formula phi, we have L proves phi if and only if L proves the skolemization of phi. And sometimes we also call L admits a skolemization, or you may hear that I say L has a skolemization, the logic has a skolemization. And maybe this is a good place here that I mention something about this definition and the usual skolemization that maybe you are more familiar with, the model theoretic view. Both of them are talking about the same thing or similar things, because here in the proof theoretic view, I am taking a strong quantifier, I'm taking for all quantifier and replacing it with new functions. But what you may have in mind or be more familiar with is just taking existential quantifiers and replace them with new functions. But what I say that both of them are talking about the same thing is here, because what I define is that L proves phi if and only if L proves phi to the S, skolemization of phi. And then if I take the contrapositive of this, it says that L does not prove phi if and only if L does not prove phi S, which means that there exists a model for negation. There exists a model M such that M is a model of negation phi if and only if there exists a model M prime such that M prime is a model of negation phi S. So you see a negation here is playing a role, and the negation is responsible for the exchange of existential and quantifier and removing them. So what I wanted to mention here is that the proof theoretic view is basically the same as the usual model theoretic view. Yes, and about related work, so there is a very old work by Mintz. And this is, I think, the best result that we have for IQC, which says that for pre-next formulas, skolemization is sound and complete in the setting of IQC. So not for the whole IQC, but for the subset of pre-next formulas of IQC, we have a skolemization sound and complete. So because I mentioned that the skolemization in intuitionistic logic is difficult, there has been some work by other people, for instance, by Raheleh and Matthias, that they consider alternative methods of skolemization. They change the method that we have skolemization, they change it a little bit, and then they study this kind of alternative skolemization in intuitionistic logic, in intermediate logics, and see whether they get a characterization or not. And another direction of research goes to not considering intuitionistic and super-intuitionistic logics, but also considering other logics, such as substructural and fuzzy logics, where Matthias George Metcalfe and Peterson, they have worked on this direction. Okay, so I started this work when I was postdoc in Utrecht, and so I knew that Raheleh had some work in this skolemization. And so when I was reading about skolemization in intuitionistic logic, some thought came into my mind, and I thought that this is a very natural thought. And of course, people have done this research before. And the thing that came into my mind is that what if I strengthen IQC in a way that the quantifiers and connectives, they commute freely? And in a sense that I get the pre-next normal form for every formula in IQC. So I add some axioms to IQC, or I strengthen IQC in a way that each formula will have a pre-next normal form. So you see, I'm mimicking the method that we have for CQC, and I wanted to strengthen IQC. First of all, I didn't know whether this is going to be a trivial logic, like for instance, does it go to CQC? And of course, I thought this has been done, and Raheleh told me that it's not, or she is not aware of any work. And this is the start of our research. And the start is that we add these axioms to IQC, we strengthen IQC, and then for the new logic, we study it, and we see how the new logic, how strong the new logic is, and the main question, does the new logic have a skolemization or not? Okay, so this was the first part of the talk, the motivation, and now I'm going to talk about this strengthened logic that we call the logic of quantifier shifts, QFS. So yes, when we consider the commuting of the quantifiers for all and there exists with the connectives, conjunction, disjunction, and implication, in intuitionistic logic, three of these quantifier shifts or these commutations, they are not provable in intuitionistic logic. And those are the ones that we are interested in. So the definition goes as follows. Suppose A of x is a formula and B is a formula such that the variable x is not free in B. We are in first order language, of course. And then consider these three axioms. The first one is constant domain, which says for all x, A of x or B implies for all x, A of x or B, which we call also denote by CD. The next one is quantifier switch, and it says that for all x, A of x implies B, then there exists x such that A of x implies B. So therefore all on the left-hand side can go out by using this axiom. And the last one is existential distribution, which we call and denote by ED. And it says that if we have B implies there exists x A of x, then there exists x B implies A of x. Again, the existential quantifier coming to the front. And as I mentioned, these are the only three axioms which are not provable in IQC. However, in CQC, both of these formulas and their converses are provable. So the commutation of the quantifiers and connectives, all of them are provable in intuitionistic logic except for these three. And you can imagine that if I add also these three as axioms to a logic, then we will have the quantifier exchange and with the connectives, and this is what we wanted. And this is what I'm going to do. I'm going to add these three axioms, CD, switch, and ED, to IQC and denote it by QFS, and we call it the logic of quantifier shifts. And I'm going to spoil the whole talk by giving you the main result here. That what we get is that, so what I wanted at the beginning, I wanted to see whether this logic has a skolemization or not, and it turned out to be a very stronger result, which made us really happy because we gave a characterization of all the intermediate logics that have a skolemization. And the theorem says that if you think about an intermediate logic between IQC and CQC, it has a skolemization if and only if it is above this QFS. So QFS has a skolemization. This is what we wanted to show. And moreover, any logic above it has a skolemization, and below it cannot have skolemization, which is I think it's a nice result. So before going to the result and talking about the logic, I wanted to define some preliminary notions, which you may be familiar with, but because they're very basic notions, I'm going to go through them quickly. So the first definition is about Kripke frames. A Kripke frame for IQC is a triple W, some relation which we show by less than or equal to some function D. Sometimes this is also, the relation is also denoted by R, such that W is the set of worlds and it is non-empty. This relation is a binary, reflexive, and transitive relation over the set of worlds W. And D is a function which assigns to each W, each world, each small w in the capital W, a non-empty set D of W, which is the domain of W, and it has this property that if a world W is below some other world W prime, then the domain of the lower world is contained in the domain of the upper world. And the Kripke model for IQC is a quadruple, which the first three form a Kripke frame, and V is a valuation function in the usual sense, which I'm not going to define, but you can, if you're familiar with, you know what this valuation function is doing for relations and functions and propositional variables. And then we have the definition. Formula A is defined to be valid in a frame F, denoted by F validates A or forces A, and valid in a model M, denoted by M forces A as usual. I have brought the definition here, but of course we are not going to go through all of them. The nice ones, the important ones, are existential and for all. So I say that there exists X, A of X is true in a world if there exists some member of the domain of that world such that, so this member D, such that in that world A of D is true. So existential is on spot. You can define the validity of an existential quantifier on the spot, on the world. And for all is different. So in a world V, I say for all X, A of X is true if I consider, it's a global thing, if I consider all the worlds above W, and for any world above V, sorry, for any world above V, I consider every member of the domain of that world W, such that for every of these elements in W, we have A of D holds. So a Kripke frame is linear if it is linear, meaning that for any two worlds in a set of worlds, either one is below the other or the other one is below the other one. And a Kripke frame is constant domain if, again, the domain of all the worlds are constant and they are equivalent to each other. So these two are the Kripke frames that we are interested in. Oh, and one other notion, for any world W, I define this notation. So this notation means that all the worlds above W. Yes, maybe here is a good point to talk about. So I talked about skolemization fails in IQC. But I didn't give you an example of the failure of skolemization in IQC. So the axiom CD that I mentioned before, which was this axiom, This is not provable in IQC, and the reason is as follows. It's very easy to show by a Kripke model only consisting of two worlds, as shown here. So it is not provable in IQC, but the Skolemization is. The Skolemization of the formula, I look at the positive occurrences of universal quantifiers, which is only the for all quantifier on the right-hand side of the implication, and I introduce a new constant c. The Skolemization is going to be this formula, which is obviously provable in IQC. So this is an example of failure of Skolemization in intuitionistic logic. So now I want to define a class of frames, because the first step of studying the logic of quantifier shifts, I wanted to study the semantics. And by semantics, I mean Kripke frames and Kripke models. So the definition is as follows. Let F be a frame. And we define WF as being this condition that for any world W, the set of the worlds above W is well-founded. So this WF is for well-founded, and CWF is for conversely well-founded, which is defined similarly, which says that for every world W, the set of the worlds above W is going to be conversely well-founded. And well-founded means that for any subset of this set, it has a minimal element, or it doesn't have a descending chain. And conversely well-founded means that it does not have an ascending chain. One important remark here is that we can find a frame F that satisfies this WF, and the relation is not well-founded on W. So consider this chain, which is a descending chain, V0, V1, V2 up to infinity. And then if you consider this frame for any world that you consider, and you take the worlds above it, it is going to be a well-founded set. Of course, this relation is well-founded, but the relation, this less than or equal to relation on W, is not well-founded because it's, as you can see, we have a descending chain. And this was important because when I was finishing the work, I just, so we had well-founded and conversely well-founded in the definition, and then I noticed that, oh, this doesn't make sense, and I had to change the definition to these new definitions so that this evil thing does not go through our frames. And now we define a rich class of frames for QFS and its fragments. So this curly F I want to define. It is the class of the following Kripke frames, which are closed under disjoint union. So any frame in F is constant domain with the domain D, this curly D, and satisfying one of the following conditions. So a frame F is in this curly F, either when it is constant domain, and either it has only one element in the domain, or second, it has more than one element, but it is finite and linear. And three, if D is infinite, then first of all, it has to be linear and it should satisfy both WF and CWF. So for any world that you take, the set of worlds above them should be both well-founded and conversely well-founded. And there are two more class of Kripke frames, curly F sub ED and curly F sub switch, SW, which are defined using this curly F, augmented with the frames of also the following form. Constant domain again, linear, infinite domains, and satisfying WF. And for switch, we have the CWF. So what I have defined here is a class of Kripke frames, this curly F, and curly FED and curly F switch. And now, so these are the axioms that we knew before. So these are in gray so that you recall them, but these are not new information. So the theorem, the very nice theorem, is the frame characterization. Based on the names of the class of frames, this is what you would expect, that let F be a frame. The first one says that F validates CD if and only if F is constant domain. This is a known result. The other ones is what we established, is that F validates the axiom ED if and only if F is in the class curly F sub ED. Similarly for switch, and for QFS, for the whole logic, we have F validates QFS if and only if F is in curly F. So this was one of the very nice results that we established. And I think this result, and also the one that I'm going to mention later, I was talking to Hiroakira Ono about these things, and after writing up our draft, and he was mentioning that many results from 80s and 90s, they have established some parts of this result and the theorem that I'm going to mention later. So not all of these are new, that even some of them are in Japanese and also but Hiroakira Ono, he knew of all of them, and it was very nice to see the kind of works that has been done before. So the theorem, this theorem is going to be very detailed, and it's a huge part of the paper. But I wanted only to show you one example of one side of one of the bullets. So consider this frame, the left one, which is an ascending chain, W1, W2, W3, and all of them are constant domain. The domain is D. And I wanted to show that the left frame, this one, is a frame for ED. ED is here on top. And so I have to show that, and it is enough to show in the root, in W1. And I wanted to show that if W1 proves B implies there exists XA of X, then in W1, the right part of the implication is going to be true too. So suppose I have B implies there exists XA of X in W1. So I'm going to hand wave here. I hope it will be clear and you get an idea. So two things will happen. Either this B is never true in any of these worlds, in W1, W2, and so nowhere this B is true, then because the domain is constant, so because B is never true, you can just choose some element small d and say that for this D, there exists X, B implies A of X, and for this existential, to witness this existential, you use that element D. And you use this D because it is present in all the domains of all the worlds. But the interesting case is that this B, the formula B, is true in some worlds. And then this is the place where we use the well-foundedness. Because it is true in one world, we know that there exists a minimal element, a minimal world, such that B is true in there. So there is a minimal element such that B is true there and above, and below that B is not true. In this world, we take this world and take an element of this, because B implies there exists XA of X also holds here. It means that there exists an element of the domain such that A of that element is true. We take that element for the witness of this existential. And you can see that it is easily shown that in W1, this existential formula holds. And the right one is a frame for QFS. So far we are very happy because we have a frame characterization, but then we get an interesting result about frame incompleteness. So we say a logic L is sound and complete with respect to class C of Kripke frames. So let this C be a class of Kripke frames. And logic L is sound incomplete with respect to this C for any formula phi, we have L proves phi if and only if this class C validates phi. And then using this definition, we can define a logic is frame incomplete if there is no such class C as in the above definition. So if there is no class C of Kripke frames such that L is sound incomplete with respect to C. And the interesting result is that all of these following logics, QFS, IQC plus CD and switch, and IQC plus CD and ED, they are all frame incomplete. So I'm going to sketch the proof for QFS. And to show that the logic QFS is frame incomplete, based on the previous definition, we have to prove that for any class C of Kripke frames for the QFS, for the logic, we have a formula. We can find the formula phi such that phi is validated in the Kripke class C, but is not provable in the logic QFS. So we are looking for this phi. And we claim that an instance of this formula, lin or oop, so lin is linearity, is this axiom C implies D or D implies C. And this oop is one element principle, which says that if there exists xa of x, then for all xa of x. So an instance of this formula phi, we are going to claim that it works. How does it work? So the first part is that remember that if we were talking about a frame F, and if a frame F validates QFS, then we saw that it should be constant domain. And this is because of the axiom CD. And moreover, F is either linear or its domain is just a singleton, which is basically what is saying here in the formula lin or oop. Which means that F validates all instances of the axiom lin or oop. And there is an instance of this formula such that QFS does not prove it. So basically what we are showing is that these two points together will prove that QFS is frame incomplete. So this is the sketch of the proof. The first one was easy by just looking at the frames that validate QFS. And the second one is, again, very easy model. We can easily consider this model, which only has three worlds, W, V1, V2, and it's a model of QFS, but you can see that in the root, lin or oop does not hold. So I'm not going to go through the model, but the domain is constant. Domain of all of them are going to be this small a and small b. R is a unary predicate, and P and Q are going to be nullary predicates. And then we will see that in W, an instance of lin or oop does not hold. Okay. So this is interesting that we get frame incompleteness for QFS. And then after that, we were thinking whether we are, because we are also talking about fragments, we were thinking whether we are talking about separate, distinct fragments, or some of them are going to be equal to each other. And then our theorem was, it guaranteed that all of them are distinct. The theorem which says that, so by CD and switch does imply or does not imply some formula, I mean that adding CD and switch to IQC does not prove the axiom ED. And similarly for switch, so if you add CD and ED to IQC, it does not prove switch. So all these fragments, QFS, IQC plus CD and SW, and IQC plus CD and ED, all of them are distinct. And we have, as I mentioned, frame incompleteness for all of these logics. Yes, so, but this is also interesting that IQC switch is very strong, meaning that if we add switch to IQC, it proves CD, and somehow if you have switch, you don't need to have CD as well. And another very nice result is that ED does not prove CD. Again, these results here and there were some results in 80s and in 90s in different papers. So not all of these results are by us. Of course, we could reprove them easily, but some of them are known before. Okay, I think, yes, this is the end of the semantical part of studying QFS. But so far, I've been talking about the logic QFS and its semantic, its frame characterization, framing completeness, all of them with respect to Kripke frames, of course. But I haven't talked about the Skolemization that I motivated this talk to, right? So I started with Skolemization, and I said to you that we are going to talk about the Skolemization, but so far we have not. And at this point, so I mentioned this research we started with Rosalie, and at this point, we were thinking about one problem, namely the following, that if I have a formula A, which is in pre-next normal form, and if QFS proves A, does it also imply that IQC proves A or not? And why we're thinking about this, the reason is that because of the result by means, then because we know that for IQC, for the pre-next fragment, we have Skolemization, then we would get Skolemization for the whole QFS. So this problem says for the pre-next fragment of QFS, but we mentioned that each formula in QFS will have a provably equivalent formula in pre-next normal form. So we would get Skolemization for the whole QFS, which would be very nice. And yes, if these things are true, then we would get as corollary that QFS admits a Skolemization. And I think you're expecting what's coming, which is, unfortunately, this is not the case. So this thing is, so the pre-next fragment of IQC and QFS are not the same. And for instance, one example is the following, that QFS proves CD. And you can just go step by step and write it in pre-next normal form. QFS proves this formula, which is in pre-next normal form. However, it's very easy to show that IQC does not prove it just by taking a model which has only two words. And it's defined as following. Okay, so this didn't work. And at this point, we are at the point that we don't have we have established framing completeness, which means that we don't have a nice semantics. We cannot work well with the semantics to prove a Skolemization. And we don't have a good proof system. What do I mean by a good or well-structured proof system? I mean, for instance, a sequent calculus, which is cut-free, or it is analytic. Because the obvious sequent calculus that comes to mind for QFS is taking the sequent calculus for IQC, the LJ sequent calculus, and add these three axioms as initial sequence to the sequent calculus, which of course it's not easy to show. So this may not have, it's a good probability that it does not have cut elimination. And I'm not saying that we don't have a cut-free or analysis sequent calculus for QFS. I'm saying that we don't know of any. Maybe there are, but we have not found them yet. But we are at this point. And so proof theory does not help, model theory does not help. So we were thinking about how to prove Skolemization for QFS. And I was giving this talk, and Matthias was in the audience. And after my talk, he came to me and said that Juan Agurela and himself, they have a proof system, and Skolemization can be easily done using their sequent calculus. And it has been 2 years after that discussion that Matthias said it's going to be very easy, and we finished this after 2 years. Yes, so the sequent calculus that Matthias proposes in this paper at 2019, it is a sequent calculus for first-order classical or intuitionistic logic, which relaxes the usual quantifier inference restrictions that I'm going to show in the next slide. But it doesn't have these usual restrictions, which will go into some calculus, which will have unsound inferences. It lacks local correctness, but the good thing about it is that it has global correctness. So it introduces some lies, but they make sure that every lie that has been introduced during a proof, in the end, it will be cleared. This is the sentence that they use for describing their sequent calculus. And yes, we are going to use this sequent calculus. So for that, I need to give some definitions. I try to go through them quickly. So an inference is a quantifier inference if the principal formula has a quantifier as its outermost logical symbol. For instance, this one, which has for all as the outermost logical symbol, is a quantifier inference. The characteristic variable of an inference is A. For instance, in this inference, if you look at it, it is A if the inference yields a strongly quantified formula. So this formula here is for all x A of x, and this for all is strong. So this A, small a, is going to be a characteristic variable. And if pi is a derivation, we say that b is a side variable of a in pi, written as a is less than b sub pi. If pi has a strong quantifier inference of one of these forms, so a strong quantifier meaning that for all is on the right-hand side or there exists is on the left-hand side, and this a, as you see here, is going to be a side, so b is going to be a side variable of a. This a was characteristic variable. Similarly here. So these are some notions which are useful for the sequent calculus. And let me remind what sequent calculus LK, the first order LK is. It is the extension of the usual propositional LK for classical logic, obtained by adding these quantifier inferences. And this is a very important constraint that we have in LK, and it should be in LK, which says that in existential left and for all right, the variable y is not free in the conclusion. And when I was saying that they relaxed the constraint, I was mentioning this kind of constraint. And first order LJ, the sequent calculus for intuitionistic logic, is defined as the single conclusion version of the first order LK, such that everywhere in the succedence there is at most one formula. And the sequent calculus QBF, this bold, which I show it by bold QFS, is defined as the sequent calculus for intuitionistic logic LJ, plus the adding these formulas as initial sequence. The one that I mentioned is not cut, it does not eliminate cut. And now we have this definition, which is the core of the sequent calculus. So they say that a quantifier inference is suitable for a proof, pi, if either it is a weak quantifier inference, meaning that it does not have strong quantifiers as the introducing quantifier, so meaning that it introduces a for all on the left or existential on the right. So it is suitable if either it is a weak quantifier inference or the following are satisfied. Substitutability, which says that the characteristic variable does not appear in the conclusion. side variable condition, which says that this relation less than sub pi is acyclic, and very weak regularity, which says that the characteristic variable is also, if the characteristic variable is also the characteristic variable of another strong quantifier inference, then the principal formulas should be the same. And I'm going to show you very briefly why they have chosen these conditions. And then they say that if they have these conditions, then they can guarantee that they have a sequent calculus which is globally correct. Yes, so for instance, each of the quantifier inference of LJ in the previous slide is suitable for every regular LJ proof. So the justification is as follows, as I promised, is that if violate each of these three conditions, it will lead to an undesirable proof. For instance, the substitutability, which said the characteristic variable does not appear in the conclusion. So here A is a characteristic variable and it has appeared in the conclusion, and we get something which is not true. From A of small a, we get for all x A of x, and we don't want to call this thing as a proof. Similarly, for the violation of the acyclicity of the this relation, this is not an acceptable proof because if you can see here, star 1 and star 2, B is less than A and A is less than B, and then in the end we get something which is not acceptable. Similarly for the third one. And then what they say is that the calculus LK++, so this calculus is called LK++, respectively LJ++. It is defined like LK, except that the constraints are on those constraints on quantifier inferences is removed. And we add the restriction that the proof may only contain quantifier inferences that are suitable for it, as defined in the previous slide, the suitability. And then this is an interesting fact, which says that all the quantifier shift axioms are provable in LJ++. So basically, so they didn't have QFS, but basically what they proved is that if S is a sequent, then LJ++ proves the sequent if and only if our sequent calculus QFS proves S. And then the very important result that we are going to use to get skolemization is the following, is that if the skolemization of a sequent, which of course I have not defined, but you can imagine that it can be defined using the skolemization of a formula. So if the skolemization of a sequent gamma double arrow delta is cut-free, LJ++ drivable, this cut-free is important, then we can de-skolemize it in the sense that gamma double arrow delta is going to be cut-free LJ++ drivable. And then using this theorem, we can very easily have the corollary that QFS admits skolemization, which is going to be very easy. I'm going to go through it quickly. So suppose QFS proves skolemization of a formula A to the S. Then because the logic proves it, of course, the sequent calculus proves it, proves the sequent double arrow A to the S. And it means that in LJ, we can prove some sequent of the following form, B1 up to Bn double arrow A to the S, where each of these BIs are instances of CD, ED, or switch, which are not provable in LJ, right? So take this sequence, and because in LJ it is known that this sequence is provable, double arrow phi implies phi to the S for any formula phi, then taking this, we can have in LJ that B1 and Bn to the A to the S is provable, and using this as phi, I can prove the following, the same formula, the skolemization of the same formula on the right-hand side. So because we are talking in LJ, it means that there is a cut-free proof of this sequence, the last one in LJ. And any cut any proof in LJ, of course, any cut-free proof in LJ is going to be an LJ++ proof. And now, so we have lifted, so from QFS, we have gone to LJ, and from LJ, we are going to lift it to LJ++, and use the theorem in the previous section that we can de-Skolemize in LJ++ if we have a cut-free proof. So in LJ++, we can de-Skolemize it. And the rest is easy because what we have done is that this B1 up to Bn, these are all instances of the axiom CD, ED, or switch. So all of them are provable in QFS, which means that double arrow A is provable in QFS, which means that QFS proves A. So this is the proof, and I'm going to finish by concluding remarks. We introduced the logic QFS by adding the quantifier shift axioms to IQC, and we showed that QFS is Kripke framing complete. And the main result that we showed is that an intermediate logic admits a Skolemization if and only if it contains all quantifier shift principles. And for future work, so we show that QFS does have existence property, this EP, and we are asking whether it has disjunction property or not. I don't know. And there can be investigation of the full power of QFS by considering other axioms which are not provable in IQC and asking whether they are provable in QFS or not. And thank you.